In this course, you will study MapReduce and YARN over a total of 3 major sections, 8 videos, and 2 hands-on labs. The objectives of the course are to provide you with the ability to describe the MapReduce model version 1. This is the classic version that comes with Hadoop 1. List the limitations of both Hadoop 1 and MapReduce 1. Review the Java code required to handle the mapper class, the reducer class, and the program driver needed to access MapReduce. Describe the YARN model, including the features of YARN and how a YARN program is run. And finally, compare YARN Hadoop 2 MapReduce 2 versus Hadoop 1 with MapReduce 1. In this course there are 3 main sections and a total of 8 videos. There are hands-on labs after the 4th and 8th video. We will first look at classic MapReduce processing based on MapReduce version 1. Then there will be discussion of the issues with and limitations of that approach. And finally we will study the architecture of YARN, yet another resource negotiator, and how YARN MapReduce 2 relates to classic MapReduce version 1. We will start with an introduction to MapReduce processing based upon MapReduce version 1. This is the agenda for the first section of the course. It deals with classic MapReduce, now known as MapReduce version 1 or MR1. The driving principle of MapReduce is a simple one. Spread your data out across a large cluster of machines, and then, rather than bringing the data to your programs as you do in a traditional programming environment, you write your program in a specific way that allows the program logic to be moved to the data. Thus the entire cluster is brought to bear in both reading the data as well as processing the data. A distributed file system, the Hadoop distributed file system, aka HDFS, is at the heart of MapReduce. It is responsible for spreading data across the cluster by making the entire cluster look like one giant file system. When a file is written to the cluster, blocks of the file are spread out and replicated across the whole cluster. In the diagram, we can see that every block of the file is replicated to 3 different nodes or machines in a cluster of machines. Adding more nodes to the cluster instantly adds capacity to the file system, and as we shall see in the next slide, automatically increases the available processing power and parallelism. MapReduce is a software framework originally introduced by Google to support distributed computing on large data sets held on a cluster of computers. The Hadoop distributed file system, HDFS, is where Hadoop stores its data. This file system spans all the nodes of a cluster. Effectively, HDFS links together the data that resides on many local nodes, making the data part of one large file system. Furthermore, HDFS assumes nodes will fail, so it replicates a given chunk of data across multiple nodes to achieve reliability. The degree of replication can be customized by the Hadoop administrator or programmer. However, the default is to replicate every chunk of data across 3 nodes, 2 on the same rack and 1 on a different rack. The key to understanding Hadoop lies in the MapReduce programming model. This is essentially a representation of a divide and conquer processing model where the file's input are split across many pieces in the map step, and the Hadoop node processes these pieces in parallel. Once these pieces are processed, the results are distilled in the reduce step down to a single set of results. If one task is very slow, it can delay the entire MapReduce job, especially towards the end of a job, where everything can end up waiting for the slowest task. With speculative execution enabled, however, a single task can be competitively executed on multiple slave nodes in parallel. For job scheduling, by default, Hadoop uses a FIFO approach, first in, first out, with 5 optional scheduling priorities to schedule jobs from a work queue. Other scheduling algorithms are available as add-ins: Fair Scheduler, Capacity Scheduler, and others. The Job Tracker master node breaks the job up into map and reduce steps, finds where the blocks or splits of the input file or files are located, and then assigns work to the appropriate worker nodes for map and reduce processing. In the map step, each worker node participating in the mapper process takes its designated block of input, reads it, and then performs the map processing on it. It produces an output file for each of the reducers that participate in the follow-up step. In the reduce step, the answers to all the subproblems generated by the map nodes are sent to a set of reduce nodes, where they are combined or aggregated in some way to produce the final output, the results of the problem MapReduce was originally asked to solve. The slide shows the execution environment and describes the application programming interfaces, APIs, that are used. We will see that a similar and somewhat compatible API environment is used for both MapReduce 1 and for YARN/MapReduce 2. This is the end of this video. In the next video we will look at the processing phases in the MapReduce process.